will do my best to 3D is an extension of a force question and asks about the speed at which you can overtake the top of the hill. Now, to understand what has happened so far in this problem, you need to understand that the car was fired forward, went over the loop, and then is over here, pulled up against this spring. So let's consider that at this moment, the car is here, pulled back against the spring, and is going to be launched to the top of this hill. We are told that the hill is a circular hill, and the car will eventually make it to the top of this hill. The hill has a radius of h, and we're asked to find what is the maximum speed the car can successfully make it over the hill. This has nothing to do with energy. And you need to know when energy is something you can use and when it's not. This is not. This problem is about force. So problems where an object is traveling in a circle and you are asked specifically about speed related to that motion, that's got to be a net force problem. The only place centripetal acceleration shows up is in net force. So if you have something traveling in a circle, you should probably consider net force as the means to go. I'm not saying that that's a universal and it's absolute, but it's very likely. It's always going to be likely when you're asked maximum or minimum speed for something traveling in a circular path, because you want to know whether it can make it through the path without, falling off. That's going to be about forces. Now, there are two forces acting on the car when it's at that point. There is a normal force upwards, and there is weight downwards. So I will make downwards positive because the acceleration is towards the center of the circle. So that will be mg minus n equals mv max squared over h. Radius of curvature is h. Don't put r, because one of you will, and you'll say, well, what if I put r? Can I still get credit? Nope, you can't. Now, this is where, when I look at students, I often can figure out who knows what I'm talking about and who's not. There are things that don't change. The mass of the car doesn't change, right? It's being shot forwards over this loop. I get to choose how fast the car goes based on how far I pull it back against the spring. If I pull it back farther, the car shoots off faster, right? I get to choose the velocity. So I can make this number bigger. On the left side, I can't change this number. This number responds to the situation. So as I make V bigger, this whole side has to get bigger. Well, there's a limit to how big that side can be. When n is 0, that's the limit. You reasoning this out is hard. I know it takes time. But I am subtracting something from mg. What is the smallest number I can subtract from mg? 0. The normal force can't switch directions. So when this is 0, I am at the maximum speed of the car. Cancel the m's, and that max speed is the square root of gh. Now, I think it probably appropriate that I talk about question E, since it's an extension of this. But is there any question about that? Okay. Question E asks, how far back can I pull the car against the spring and launch the car so that it can successfully make it over the top of the loop without jumping? So, I have to choose a reference level for this question. And I think that there are two possibilities. You might only see one, but I think there are two. I think this is a possible reference level, but I also think this is a possible reference level. I can choose either one. I am comparing two states of the problem. I'm comparing state A, where it's being launched, with state B, the top of the ramp, or the top of the hill. So, which reference level would you prefer I use? The rest of the problem, we had to use this reference level. So I could use this one. That way your answers will be similar to what you got for A, B, and C. But we could use this one because that means the reference level is 0 at the spring. Doesn't matter to me. How many of you want me to use 1 as the reference level? Okay, that's enough. So we will use 1 as the reference level. If I use 1 as the reference level here, then that means that at A, there's elastic potential energy and there's gravitational potential energy. It is above the reference level and it is pulled back against a spring. But the car is at rest. I am releasing the car from rest. So the car is not moving at this time. When it is fired upwards, it makes it to the top of that hill. At the top of the hill, it's moving. So it must have kinetic energy. It's no longer pressed up against a spring, but it is definitely above the reference level, so it's got gravitational potential. I'm going to set the energy of these two states equal to each other. So 1/2 kx squared plus mg times 3h. Look, it's a capital H, and it's 3 of them. I'm saying this not because I want to reiterate it, but because in a few minutes, this thing is going to be filled with letters, and it can become challenging. I need you to recognize that's okay. You need to rise up to the challenge, but you have to use the letters they give you, not ones you want to use. All right, that's going to equal, well, it's at the top of the hill. I kind of made it a little bit small, but they're top of the hill. That's mg times 4h. So I zoom out and it makes the pen thicker. That seems to work in the wrong direction. Would you agree? Yeah. Plus, the cart's now moving now at 1/2 mv squared, but we just solved for v. V is the square root of gh. That's what we solved for right here. So this is going to get even hairier now as we start to put all that together. Oh my word. Just pick a 1/2 kx squared plus mg times 3h equals mg times 4h, 4h plus 1/2 m square root of gh squared. That's just a whole lot of letters. It's hard to even know at this point what you were supposed to do. You were supposed to find x. They gave you all the other letters. It's like they gave you 200 for K, 1/2 kilogram for M. You know what G is, and they told you that H was 12. It's like they gave you those numbers. You can have them in there. You have to realize that the thing that they want you to find is this, and you have to do the algebra to get it by itself. Some of this algebra is not so terrible, but you still have to do it. And I've been watching you guys do algebra for a while. It is painstakingly slow to watch you guys do algebra because you're still probably doing it the same way you did it when you were in algebra 1. You're still having to show minus mg 3h on both sides. I see this in your work, and I don't want to stop, but this is time consuming for many of you. And you get nervous and you stop being careful. Just take your time. Write out each step. You're probably not in a position to skip steps particularly well. Now, I see MGH in every term. Do you? So although this looks more complicated than it is, it's just 4 minus 3 plus 1/2. That's all it is. There's an MGH there, yes. But if I pull out the MGH, what's left is 4 minus 3 plus 1/2. That's what this really is. So that's 3/2. These numbers work out like this on purpose because of the way I chose them. So they all combine nice. Cancel out the 2. Solve for x. And x is 3 mgh over k under the radical. And that's the answer. That's a lot. It's a whole bunch. I think this is not an unreasonable test. All right. Next. Yes, sir.
Situation 1 and D.
Situation 1, question D. Which ball, the one on ramp A or the ball on ramp B, make it to the end of the ramp first? Explain your reasoning. Okay. Now, when I look at this picture, I am noticing quite clearly that the balls do not have the same amount of potential energy relative to the lowest point they could achieve. Do you notice that? I do note that at the end of the ramp, the balls will have the same amount of energy here, and they're at the same height. So at the end of the ramp here, they both will have the same velocity as they leave the ramp. But on ramp B, the ball, when it made it to here, will be traveling faster than when that same ball makes it to the bottom of ramp A. Would you agree with that? So I think the ball on ramp B has the chance to make it across sooner, because for the time that it's traveling along the bottom, it's traveling faster. Do you see my argument? I think that's a reasonable argument to make. But I think there's another reasonable argument as a counter. It's traveling faster, but it appears to be also traveling further. Does it look like that to you as well? So I think you can make a reasonable argument the other direction as well. This problem was intentionally ambiguous to see if you understood that for a portion of the ball's motion on ramp B, it's traveling faster than ramp A, and that will have an effect on whether it makes it across sooner. I think we could also probably agree that depending on how much faster it's traveling would also determine whether it makes it there further or not, because it has to travel further downwards to get to that lower portion. The question is, what part of this do you explain? The test graders do this on purpose. They often have an ambiguous portion of the problem. And your job is to figure out, what are they trying to get at? There's not necessarily a single correct answer. It's about your explanation. But I think if you want the best chance of getting the credit, you should focus on the obvious things and not look for the nuanced things. It is obvious that it goes faster on ramp B when it's at the bottom. It's less obvious that one might be a little longer than the other. You follow my argument? So I would say that ramp B gets it there faster because it has a period where it travels faster. It's like asking the question about having a ramp like this or a ramp like this. If I have ramp 1 and ramp 2, which ball gets to the end first? It's ramp 1. Ramp 1, the ball accelerates to its top speed sooner because it's steeper. Ramp 2, it doesn't. I think that's a hard question, but I think it's a good one. No hints. I don't know if this is on your test or not. I wrote your test like 2 weeks ago. I don't remember what I put on it. But that's a great question. It's a good follow-up. And it also brings up something I said in class, that the gravitational potential energy is path independent. No matter which path they take, the ball's traveling the same speed at the bottom. And that's an important question. Oh, that was fun. Good times. Yay, physics. I'm ready and prepared to hear your next question. Yes, sir.
4C.
All right, so this question was on a practice AP exam years ago, and then they had a very similar one on an actual AP exam. I'd say this is a good thing to be able to practice. It's got a lot of good stuff in it. There's conservation of energy, there's work energy theorem, there's all sorts of good things in here. And so I would see this as potentially a solid contender. It says a spring launcher, you just want part C. Does anybody need A and B? So just C? What's that? I don't know. A spring launcher on level ground is retracted at distance D from its equilibrium position. So the equilibrium position is here. That's the equilibrium position. So when the spring is here, there's energy in the spring. And the amount of energy in the spring would be 1/2 kd squared. Right? When it's pulled back that far, D. I'm just throwing this out there as I read the problem. It is used to launch a small box of mass m. There is a coefficient of friction of mu between the ground and the box beginning at 0 as shown. Describe what type of energy exists in this system from the moment the box is released to the moment it comes to rest at a location 3D away from 0. That's easy. It's got elastic potential energy when it's pulled back against the spring. When it's released, it transfers that energy into kinetic when it's right here. But that kinetic energy will eventually be drained away, and it will have no energy at all when it comes to rest. That energy was turned into thermal energy or something. It heated up the surface here as that energy was taken away from the block and given to the table or whatever it is. So I don't know that you'd have to talk about the thermal energy, but you should talk about the fact that the frictional force did work on the box to take the energy away from the box. The experiment is to be repeated. A student conjectures that if they want the box to travel a distance 6d, they should pull the spring back further. He suggests the spring be pulled back 2d and released. What part of the student's reasoning is correct and what part is incorrect? I love this question. It's on your test. This is the direction the test is going to start moving, because this is the direction the AP exam actually is, where you will have to evaluate a conjecture made by a student. Simple sentence here. There is something that is right about the student and something that is wrong about the student. What's right about the student is that you will have to pull it back further. It will take more energy to travel that distance. That's right. But if I pull it back twice as far, that's 4 times the amount of energy, right? If I pull it back a distance 2d, because the 2d is squared, that's 4 times the original amount of energy. But the thing only travels twice as far. I'm saying that because if it travels twice as far, are we convinced we need 4 times the energy to travel twice as far? I don't know. The work done is going to be minus mu mg times whatever the distance is it travels. If this is how much energy the car has the second time, and this is how much energy the car had the first time, well, the first time, 1/2 kd squared had to be equal to mu mg times 3d. That's what x was. If I have 4 times the energy, I think it's going to go 12d. So I don't think I need to pull it back that far. I think I have to pull it back something less. Probably square root of 2d would probably be the best way to go. But I didn't ask that. Oh, question C. If the spring is actually pulled back a distance of 2d, find an expression for the actual distance to where the box comes to rest in terms of d. Have we done that? Now, if you don't understand why I did this, that's reasonable. It's reasonable to not understand why I did that. So I would like to explain that if you want to see it. So here's how I would explain it to you. would you agree that the box has kinetic energy when it's here? And that kinetic energy would have to be equal to 1/2 kd squared for trial 1. Is that true? Are we all good? Work equals the change in kinetic energy. So the change in kinetic energy is going to be K final minus K initial, which is 0 minus 1/2 kd squared. That good so far? Well, that has to equal minus mu mg, the force of friction, times 3d. Those have to be equal. The work done by friction is the force of friction times the displacement times the cosine of the angle. So what I did was 3 buckets, right? The box is sliding this way. The force of friction has to be that way. So force of friction, mu times the normal force. Distance the box traveled, 3d. Angle between the frictional force and displacement, 180 degrees. So mu mg times 3d has to equal 1/2 kd squared. All things being equal, if the only thing I change is how far back I pull the spring, well, that looks to be 4 times more energy. Right? The 2 squared, pull it out, pull the other things to the right. We talked about how to do that. This is the original amount of energy, which means by the fact that these are equal, that'll have to be 4 times mu mg times 3d. This isn't going to get bigger because of the cart, but 4 times 3, that'll mean it'll go 12d. 3 times, it'll go 4 times further. How was that? A little much, maybe, for this test. Not out of the question, mind you, but a little much maybe for this test. Question A and B, though, I have no trouble with those. And I don't really have trouble with this because I think if I had maybe taken D and broken it up into smaller parts, that I could have gotten this out of you. Does that make sense? Like if I'd asked what was the work done by friction, you would have been able to do this. If I had asked to compare that to the amount of energy that the block had, you would probably be able to do this. This might have been tough, but this might be what it takes to go from a 4 to a 5 on the AP exam. And I don't think that's an unreasonable extension for people who are trying to get a 5. You follow what I'm saying? So I'm okay asking it. You have to budget your time, I think, on the exam.